law states that V voltage equals I times R resistance. So V voltage, I current, and R resistance. We can think of voltage like, if we imagine this as an analogy of a pipe with some sort of restriction, the voltage is like the pressure that it's being forced into here, how fast it's being forced in. Current is the amount of fluid flowing through, and R is like the size of the restriction we're trying to push it through. So let's have a look at a practical example of this. Say we have a circuit with a voltage, 20 volts, capital V, because it's the name of a person, and we have some resistors. This is the symbol for a resistor. This is the British symbol for resistor. There is an American symbol which the software we're going to use uses. So this is a circuit, and we've got 50 ohms, Greek ohmic symbol, 20 ohms, and 30 ohms. Now the total resistance here, R and small subscript t, is going to be equal to R1 plus R2 plus R3. So this is R1, R2 and R3. Therefore RT is going to be equal to 100 ohms. We know from the formula of above that the total current in the circuit is going to be equal to the voltage divided by the total resistance, and that's 20 divided by 100, which equals 0.2 of an amp, capital A. We can use this because this is the current flowing in the circuit. The current in a series circuit, when the resistors are connected in series like this, is the same wherever we measure it. Because if you imagine this is like the particles of water flowing through a pipe, they've all got to travel through. They can't get out anywhere. They've all got to travel through. So if there's 0.2 of an amp here, it's got to be 0.2 of an amp here and here and here. So this allows us to work out the voltage across each of these resistors. So if we wanted to measure and put a voltmeter in, we'll call that V1, then we can work that out, because V1 is going to be equal to, well, we know Ohm's law says that V equals I T times R1. In this case, that's 0.2 times the resistance of R1, which is 50. So 50 times 0.2 is 10. We do the same with V2. V2 is IT, the total resistance, times R2, 0.2 times 20, which is 4. So it should be volts. And then V3, the voltage here, equals IT times R3, which is 0.2 times 30, which is 6 volts. Now if we add all those up, 10 plus 4 plus 6, we get 20 volts total. And that's true in a series circuit. All the resistances should add up to the total resistance. Let's have a look at simulating that in a piece of software. So if you're logged into National Instruments Multisim online, then what we need to do is to draw that circuit is first of all to get a voltage source, DC, then to get resistors. Now resistors are drawn in the kind of American style. If you want, you can just hit copy each time and it puts another one there. It's a bit quicker. Obviously got to value them all in a minute. Wire them together. Just wait for it to go to the wire symbol. Click once. Wait till it goes to another and a circle appears there, and click and it'll join. Click. And then now when you have got them there, you can modify them by pulling them down to make them look a bit neater. Pulling it to the side. Unfortunately, with any of these softwares that are based on something called Spice, they won't work unless you actually use a ground. Now in the real world, putting a ground here would actually make this circuit pretty ineffective. But for the sake of the simulation, we need to put a ground. Now you'll know when the ground's in, because as soon as you click there to put it in, this node here, this wire, will change to node 0. That's normal. If you've got it in the right place, your ground should be on node 0. We need to change the value of our voltage. We were 20 volts. We can either move it there with a slider or come across here and change the value over there. And then click away from it once you're done. The resistor is the same. This was, in our example, 50. This was 20. And this was 30. We can alter these names if we want to, if they want to make them something more meaningful, but at the minute they're okay. So we could change it to something like load resistor or a heater resistor or something like that. But now we want to measure the voltage around this. Now this is where it gets a little bit more challenging compared to some other software, but it's very usable still. So if we put a voltmeter, well, current meter to start with. Shouldn't really matter where we put the current meter. It should read the right value. So to actually make this work, we have to simulate, like turn the circuit on. If I turn it on, 200 milliamps, and that's what we found from our calculation. It was 200 milliamps, 0.2 of an amp. So the next bit is to get some voltage readings. This is where it can be a bit confusing. So we can stick a voltmeter there. I'll just move this out of the way, it's still reading there. So now it's reading 20 volts, which is not what we expected for R1. We expected 10 volts. But that's because it's reading the voltage here with respect to ground. It's not measuring the voltage across this resistor, it's measuring it from here down to ground, basically across the battery. Obviously when you have a multimeter you have two probes, and we've just got one probe here. And if we look, if I click on the voltmeter, if we look over here, in very greyed out it says voltage reference ground. We don't want it to be referenced to ground, we need it to be referenced somewhere here, like we're putting the meter across here and here. Because when we see a multimeter like this, it always comes with two leads, a red one, which we represent here, and a black one, which represent here. If we stop this, the way we do this is to put what's called a voltage reference in, and put it there. Now when we go to this voltmeter, we see where it says with respect to ground, we can change that to respect to ref 1. Now when we do the simulation, it's now reading 10 volts between there and there. I'm going to fast forward and put the other ones in. So this can easily get out of hand pretty quickly that we've got ref 1, ref 2. We can see them here, but on a more complicated circuit we might have to give some more meaningful names to these probes, like load voltage or something like that, something that refers it to this. So we need to make sure each time, we know this one here is referenced to ref 1, so it's measuring the resistance across at R1. The voltage 3 probe is referenced at the minute to ground, but we need to reference it, look, to ref 2, and PR4 we need to reference that to ref 3. That should now, once we simulate it, 10 volts, 4 volts and 6 volts, just like we got in our calculation, and current, so that's exactly as we found it in our calculation.